All right, welcome back. Let's talk about why the fundamental theorem of calculus part 2 works. Remember, the statement was this, that if you do the derivative of the integral from a, where a is a constant, to x of f of t dt, where f is a continuous function, that you get just f of x back out. Okay? So, why? Well, you just check. So d by dx of this integral from a to x, f of t dt, by definition is this limit quotient. The limit as h goes to 0, where you plug in x plus h into the function. So that would be the integral from a to x plus h, f of t dt, minus what you get when you plug in x, so a to x, all divided by h. So it looks pretty hairy. But there's a lot of cancellation that's going on there. That first integral, we could write it as the integral from a up to x plus the integral from x up to x plus h. That was one of our theorems about integration. So we integrate out to x, and then we finish going all the way to a plus h. We still have to subtract off this, the integral from a to x, f of t dt, all divided by h. And you notice this term will cancel this term. All right, so let me just recopy. So it's the limit as h goes to 0, 1 over h times the integral from x to x plus h, f of t dt. Now we're going to use the fact that f is continuous. So when h is really small, so for small h, and whenever t is in this interval from x to x plus h, which it is over here, okay? So that's a very small interval. Because it's continuous, then all the f of t's are really close just to f of x. Okay? Now, in fact, you can control what the error is, and you can then make what I'm going to do rigorous, but that's the idea, that for very small h's, since f is continuous, f of t can't change very much, and all the f of t's are close to f of x. So this guy here, if we continue it, will be approximately the limit as h goes to 0, 1 over h, the integral from x to x plus h. All the f of t's are super close just to f of x. Okay? And now, because x is a constant as far as t is concerned, right? T is the variable that's changing in the integral. It pulls out of the integral. So it'll be f of x all over h times the integral from x to x plus h of the function 1. Okay? Now that function is easy to integrate. The antiderivative is just t, so we get t evaluated from x to x plus h. So, since this is an area of a rectangle, it's no surprise that what we get, the x plus h minus x will just be h, so they cancel. And then all the h's are gone. F of x is a constant as far as h is concerned, so the answer is just f of x. So remember, the very start of this was the derivative of the integral from a to x, f of t dt. And what we showed was that that derivative was approximately f of x, and it turns out the smaller h is, the better the approximation is, and in the limit, it actually becomes exact. So that's why the theorem works. See ya.